Hello, Amitabh. Can you hear me? Γεια σου, ρε μαν. Περιμένουμε εδώ τον κόσμο να μπει.
Τι λέει?
Καλά.
Τι θα πείτε σήμερα?
Για privacy πράγματα. Δεν τα ξέρω κι εγώ, θα μας τα πει εδώ το παιδί.
Ωραία.
Αλλά δεν νομίζω ότι μας ακούει και κάποιο θέμα υπάρχει. Amitabh, can you hear us? I can't hear you.
Hello.
Oh, hello, Amitabh. How are you?
Yeah. Can you hear me?
Yes, I can hear you now.
Great. So I'm good.
Very good. It's nice to have you here. So can you try sharing your screen just to make sure we can see your slides when we're ready to start?
Yep, doing that just now. So multiple rounds. So these green boxes are the half mix boxes that I said. So these are the only ones in the pool. And these other boxes, so in a mixed transaction, it takes one from the pool and the other normal one. Yeah. This can be external, or this can be output of a remix also in this case. Yeah. So this can be also an output of a mixed transaction, and the other is always a pool transaction. Yeah. So this is how you will do. So if you look at it, 50% of the time there is an extra transaction needed, yeah, to add it back to the pool. For example, here I'm adding it back to the pool. So, but that is okay, right? So this is how the protocol should be used and how it looks at a high level. And I'll leave it for a second before I move to the next slide. So yeah, so let me now show you how we are doing this, right? So we are doing something very similar to QuizQuiz, but we are using slightly different proof techniques and slightly different constructions of the boxes itself, right? So we are using something called Sigma protocols. So I'll just first discuss what is Sigma protocol, although most of you will be familiar, but just to be sure that we are on the same page. So there is so it uses the concept of NP statements, which I'll not get into detail here. So there is a statement and it has a witness that it is a member of a set. So S is the statement, and X is the secret witness for X, right? And the prover P is given this S and X together, the secret along with the statement, and the verifier is only given the statement. And the Sigma proof of knowledge is a proof of knowledge of X such that some statement S of X is true, right? Where S is our statement. So without going to details what the statement is, right? Because it's kind of an abstract design. So prover sends a commitment Z to the verifier. It's basically a three-step protocol. Then verifier sends a challenge back to the prover. And then prover sends a response back to the verifier, right? So it's a three-step protocol. And finally, the verifier does some computation on these three values. And then if the output is true, then it accepts the proof, right? So this computation is also kind of abstracted away from this definition. And then we call it a PK3x, right? Just for shorthand notation, yeah, to save space. I'll just call it PK3x such that S of x is true, because it's a 3-round proof of knowledge. And similarly, we can define PK1x, right? So one is kind of implicit, so I'll not even write one. I'll just say PKX is a 1-round protocol, which using the similar concept that instead of having 3 rounds, what happens is that there is no challenge from the verifier. All the 3 are sent to the verifier in one step by the prover, right? So it's a 1 round where prover sends a tuple to the verifier, and the verifier accepts if this tuple outputs true from a computation, right? So that is a 1 round PK, right? So that is just the notation. I'll get into the actual protocols in the next slide. And the primitives that we have is the first primitive we have is a proof of knowledge of discrete log, right? Which is basically a type of Schnorr signature. So it's a 3-round proof of knowledge of discrete log where somebody proves that I know x such that u is equal to g to the power x, yeah, for some unknown x, and g is a generator. And the second is also a variation of this proof. It's basically a two parallel runs of this proof where you prove 2 things, right? You prove that I know x such that u is equal to g to the x, and I know x such that v is equal to h to the x, and both these x's are the same, right? So they are the x is the same in both these proofs, right? That is the third thing that he's proving. Yeah? So he's basically proving 3 things. He's proving the discrete log of knowledge of discrete log of u to the base g. He's proving discrete log of v to the base h, and he's also proving that the 2 discrete logs are equal, right? So that is just a parallel run of this above proof. And the third primitive we need is a OR construction, right? So basically, if I am given a 3-round sigma protocol for some statement foo of x, and another sigma protocol for another statement bar of x, then this is a very, very efficient technique, yeah, to combine this into another sigma protocol, which is basically an OR of the 2. So what happens is that using this, we can prove that I know x such that one of them is true without revealing which. Yeah. So the verifier will be convinced that yes, one of them is definitely true, but the protocol is zero knowledge in the sense that absolutely no information leaked whether the foo of x is true or bar of x is true, right? And basically, this should be thought of as a single protocol, not as 2 protocols, right? So the verifier will just verify it in one step. And the fourth primitive we need is a Fiat-Shamir transform, yeah, which is also a well-known primitive. So basically, what it does is that it given a 3-round proof of knowledge of any statement x, such that foo of x is true, we can convert it into a 1-round proof of knowledge of x such that foo of x is true. Yeah, it's a very simple way. So idea is that we just compute the hash of the input as the challenge, right? So the verifier's role is replaced by a hash function here. That is the idea. So without going into details, you can refer to the literature if needed. And this one is called proof D-log. So in Ergo and in the paper, this proof of discrete log, the first one is termed as proof D-log. Yeah, and later on also I'll use proof D-log whenever there is a confusion. And similarly, this is called a proof of Diffie-Hellman tuple, yeah, or proof DH tuple, because if you look at it carefully, you will see that actually these form a Diffie-Hellman tuple, yeah, HN, U, V, G, and H. These form a Diffie-Hellman tuple. So moving on, what we finally have. So let's first assign 4 numbers, yeah, G, U, H, V, yeah, which is a tuple of the form G, G to the X, G to the Y, G to the XY. So U is basically of the form G to the X, H is of the form G to the Y, V is of the form G to the XY. And typically Alice will know the secret X and Bob will know the secret Y in this setting. Yeah. So suppose Alice knows X, Bob knows Y, and then we write these 4 values as this, right? Then what kind of proofs we can construct from the primitives we already discussed in the last slide, right? So first of all, we can construct a proof of knowledge of X such that U is equal to G to the X. Right? So simply a discrete log of proof of discrete log of U to the base G. So we'll write this as proof D log GU. Yeah. Similarly, we can do the same for Y also, right? We can do Y H to the base G, whose discrete log is Y, and this will be proof D log GH. Yeah. Similarly, we can also create another proof using the DH tuple idea, where U is equal to G to the X and V is equal to H to the X, right? And where Alice will prove knowledge of X such that this is true, right? So only Alice can do this proof, yeah, if you look at it carefully. And similarly, we can swap H and U in the above, and we can also create another proof DH tuple, right? So where Bob can prove knowledge of Y such that H is equal to G to the Y and V is equal to U to the Y. Yeah? So here, if you look at it, we are just kind of swapped HU. Yeah. So this is, we just call it the dual of the above. Yeah. For lack of a better term. And finally, we can. So there are many more combinations, right? But I'll just describe one more and I'll stop. So finally, we can combine this. This, for example, we can combine this here and this. Yeah. So proof D log GH and proof D log GHU. Yeah. And then using the OR construction that I said. Yeah. So basically, it's a proof knowledge of X or Y such that either this is true or this is true. Yeah. And we can write it like this. Yeah. In the smart contracts, for example, we'll write it like this. Yeah. And mathematically, kind of, we'll denote it like this. Right. And we actually need only these two. Right. The rest are kind of just given for examples. Right. And we only need these two in our ZeroJoin construction. Right. So idea is that if you look at it, I'll first just remove this. So X or Y kind of seems ugly, right? And like this. So I'll just substitute with some question mark, right? So we can just say that proof of knowledge of something such that either this is true, this is one proof, and similarly proof of knowledge of something such that this is true, right? And if you look at it, this can be proved by Bob, right? This is basically a copy of this, right? I've just replaced Y by a question mark here. So this can be proved by Bob because he knows Y. Yeah. And this can be proved by Alice and Bob both, right? Depending on which side we are proving. So Alice can prove this side, and Bob can prove this side, right? Because this is this part, right? And this is the left part. This is the right part. So since it's an OR construction, both people can prove this, right? Alice can prove this and simulate this part, and Bob can prove this and simulate this part, right? So again, Alice can prove the left part and simulate the right part, and together she can find the combined proof that this statement is true. Similarly, Bob can prove the right part and simulate the left part, and he can combine them using an OR proof such that the entire statement is true, right? So the second statement can be proved both by Alice and Bob, and the first statement only by Bob. Yeah. So this kind of should give you enough hints already, right? But anyway, I'll just go to the next slide directly. So the basic protocol works as follows. So Alice selects a secret X. As before, Alice will always have X and Y. Bob will always have Y. And Alice so selects a secret X and publishes the coin with U equal to G to the X, right? And Bob selects another secret Y and a bit B. Yeah, so B is simply 0 or 1. And then Bob picks a coin randomly. And let's assume that he picks Alice's coin or the box. Yeah? So coin, box, and UX are the same things here. And he spends this coin along with one of his own to generate two equal value coins over O0 and O1 such that OB, yeah, so B could be 0 and we don't know, but OB has two registers alpha beta such that alpha has G to the Y and beta has G to the XY. Similarly, O1 minus B also has two registers alpha beta, but in O1 minus B's case, alpha has G to the XY and beta has G to the Y. So it just swapped. Alpha and beta are swapped in the bits, right? But since we assume that the decision diffie element problem is hard, right? So it is not possible for an outsider to decide which belongs to whom, yeah? Because Y is the ephemeral private key. Yeah? Nobody knew G to the Y beforehand. G to the Y was generated by Bob secretly. So nobody can tell which is G to the Y and which is G to the XY. Yeah? That is the whole idea of keeping the boxes indistinguishable to outsiders. And both boxes are protected by a common statement, right? A single statement. So because they have values that are not distinguishable, and because they are protected by the same statement, so the boxes are indeed not distinguishable because even the statement is same. Yeah. So this, sorry, let me just say. So both are protected by this statement, which is basically, if you just look at this statement carefully, right? If you just look at this statement carefully, and you substitute the values, right? So let's say what happens for OB, right? So in OB case, let's substitute alpha with G to the Y. So alpha is G to the Y and beta with G to the XY, right? So here G to the XY. Similarly, the right side becomes this. So if you look at this carefully now, yeah, OB, who can prove OB? Yeah, Alice can prove OB because Alice can prove the left-hand side. Yeah, and nobody can prove the right-hand side actually, because to prove the right-hand side, you need to know XY, yeah, which nobody knows. Alice knows X, Bob knows Y, but nobody knows the product of them. Yeah, so right side cannot be proved by anybody. Yeah, so what Alice can do, Alice can simulate right side. Yeah, and she can generate a fake proof. Yeah, the simulator will actually work for this, and the left side she will create a proper proof using her secret X, and she can actually spend this box using this technique. Now let's look at the other box, and I'll not get into details of why Bob cannot spend this box, right? So maybe look at the paper that nobody else apart from Alice can do that. Yeah. So I've just shown you Alice can spend it, but the other part of the proof is that nobody else can spend it. Yeah. So I will not discuss that here. Similarly, if you look at the next box, O1 minus B, and substitute the value, right? So O1 minus B, if you substitute alpha with g to the xy and beta with g to the y, then it kind of reduces to this. Yeah. And if you look at this carefully, you will realize that the right part can be proved by Bob because Bob knows why, so he can prove the discrete log of this. But if you look at the left side, this actually is not a valid Diffie element tuple, right? So nobody can actually prove this statement. But Bob can simulate this, right? The simulator will actually generate a valid looking proof because that's the property of the simulator, right? If the simulator is not able to render a valid proof, then we can use the simulator to solve the DDH, right? So if the DDH is hard, then simulator should be able to generate a valid proof even for the left statement, even though it's not a valid tuple. And using the OR, then he can combine the two proofs and also spend this box, right? So again, I'll not go into details of why nobody else apart from Bob can spend it, but I just showed you that Bob can spend this box, right? And now moving on. So now this before I move on, I'll just mention one thing. So this works when Bob behaves correctly, right? So what is the correct behavior, right? Correct behavior of Bob is given in this line. So Bob has to create two boxes with the register like this, right? So alpha beta must have this, and alpha beta in the second case must have this value, right? That's the only thing we need to ensure. The rest of the things we can verify publicly. These are the only two things we cannot verify, right? Because the DDS is hard, so we cannot really publicly verify if the register is of this form, right? So for that, if you remember, we had this dual proof, right? Bob will prove knowledge of Y using something else. So this is where the dual will come to our help. Yeah? So let me just discuss this in more detail. So again, I'm just repeating this entire thing, that what we need for Bob to behave correctly. And if you just look at the statement in a written in a different form, we just need to verify that one of alpha beta or beta alpha is of the form this, right? We don't care which one, but one of them must be of the form this, right? And the other is just the opposite of that. So we don't care of that. So then if you just go back to the slide, yeah, or the paper, then this can be done using the dual, right? Where I said, where Bob will prove knowledge of Y such that this is true, right? So I'll not go into details again here. I'll assume that you understood till now. And I'll move on to a little bit more discussion about how to implement this, right? So the above discussion, the previous discussion basically showed how to implement the protocol and how to ensure that Bob behaves correctly. But it's free. You can do it like either in the protocol layer or you can do it in the smart contract layer. Yeah. So Ergo is an interesting platform that we chose for this. So it's a UTXO based general purpose blockchain. It was kind of launched in 2019, and similar time when Ergo ZeroJoin was also developed. And it is a smart contract. It enables smart contract in a Scala-like language. It's a high-level language called Ergo script. And also has, so there are certain things that are not relevant to this talk, but I'm just gonna mention it anyway, which are interesting for Ergo. So it has non-authorizable proof of work, which is called autolycos. And it has something called storage rent also, which is basically, if a box remains on the blockchain for a long time, then eventually part of its value is taken as rent, yeah, slowly over a period of time. And when the value becomes below threshold, then it's completely removed, yeah. So it's kind of a garbage collection on chain, and it prevents long-term bloat of the blockchain, yeah. And as far as I know, this is the only blockchain that has these two non-authorizable features and storage rent. And in fact, it also has it's a neat feature called data inputs, which allows you to use other boxes without spending them. Yeah, you use them as data, which also I'll not get into details, but it has a lot of other interesting features. And it has advanced context information available for the smart contracts, right? So you can write smart contracts and you can access the entire transaction in that contract. You can assume, you can enforce inputs and outputs to have certain structure, right? So that is what we'll use to implement ZeroJoin. And Ergo Mix is basically an implementation of ZeroJoin on Ergo. Yeah. So it has basically two things. It is implemented as a layer 2 protocol, and it has a mechanism for handling fee. Yeah. So there are the two main aspects of Ergo Mix. And it's implemented as a two-stage protocol, right? So the first stage is encoding the behavior of the second stage. Yeah? And I'll not go into too many details. I'll just touch on the issue of fee. So fee is a problem in Ergomix, ZeroJoin, and QuizQuiz, right? And even in CoinJoin, because all the boxes have to have the same value, right? And if the fee is taken from the box, then the value will keep decreasing. So we cannot take the fee from the boxes. But if the fee is given from somewhere else, then the boxes, then the anonymity is leaked, right? Or the privacy is defeated, yeah, because the source of the fee can be used to defeat the privacy, right? So fee is a problem here. So ergonomics has two solutions. One is the altruistic approach, which is basically a fee is free as long as you are doing a remix. If you are doing for something else, then the fee is not free. So you are kind of sponsoring mixing. The second solution is something called fee tokens, which I'll not get into too many details. But the idea is that fees exchange for tokens, and if you control the way the tokens are transferred, right? So if the tokens are used only in remixing, and the tokens are always entering the system in a fixed quantity, then we can use this to pay fee. Yeah? We can have this idea of approximate fairness, where one party pays less fee and the other party pays more fee, but the output have the same amount of fee. Yeah? Basically, the average of the two. And this is okay as long as we control the tokens, how they enter the system. Yeah, without going to details, I'll refer you to the paper. And here is a quick view of how the implementation looks in Ergo script. Without going into again details, I'll refer you to the URL here, and maybe we can discuss it separately. So here you can see like proof DH tuple is used in a couple of places. Here is also. So this is basically the same protocol that I discussed earlier, implemented in code form. And I'll just summarize the talk now. It's more or less we are reaching the end of the talk. So there are two ways to handle fee as of now in ergonomics, which is approximate fairness and the altruistic approach, where the fee is free. And the third approach is range proofs, where basically you hide the amount completely, yeah? But it defeats the entire purpose of developing the protocol. We want to avoid range proofs. So range proof is a solution used in QuizQuiz, for example, right? And as a conclusion, ZeroJoin is basically a coin join type protocol, but non-interactive. Similarly, it's a ZeroJoin like protocol, but with a non-monotonic UXO set. It does 2 at a time. And it's like QuizQuiz, but with much shorter and faster proofs, right? It uses Sigma protocols instead of non-interactive zero knowledge proofs. And that's open problems. We have basically 2 open problems. So can we get the 2-coin structure, right? Or the QuizQuiz structure, where it's pool-to-pool transaction instead of having that extra transaction to add to the half mix pool? And are there any better approaches to handling fee? Yeah? So these are the kind of open problems as of now. Thanks for your time. Please let me know if you have any questions.
Thank you, Amitabh. So let me give one question. So how would you compare this protocol to Monero in terms of anonymity, first of all, and in terms of the other features? I know you had like a table, a matrix for comparison, but can you give a few words in regards to this? So one reason I kind of think they are somewhat the same is because you have this iterative approach where you mix, 2 outputs and then you mix again and you mix again. So what is the difference here?
So Monero has this concept of ring signatures, right? It's similar to ZeroCoin and ZeroJoin in similar ways. So there is a set of inputs, and one of them is being spent without revealing which one is being spent. But the only thing is that they have to keep track of, to avoid this double spending attack, they have to keep track of which is being spent, right? So it has only this problem that this Monero kind of follows similar approach, right? So there is a set of inputs and there are a set of outputs, and then this has to be kind of kept in the memory to prevent double spending.
Mm-hmm. Right. Okay, well, thanks for that. So I don't know if other people have questions. Okay, so we will also upload the video if you're happy with that, Amitabh, so that we can put it on the website. I think the time today was a bit unusual for most people, so some of them have told me they want to watch it remotely. So I hope you can allow us to do that. That would be nice.
Yeah, sure.
And yeah, and with that, let me also say that the seminar continues every Wednesday. We have already the schedule for the rest of October on the site, so you can take a look. It's open to everyone, and feel free to share it in your respective groups. And well, thank you very much for your time, Amitabh, for taking the time today to speak.
Giving me this chance.
Yeah, wonderful. Okay, well, have a great day and have a great evening then.
Yep, bye.